contribute. And the VOCs and the other contaminants adsorb. And that's not a misspelling. Adsorb means it's actively attracted to and attaches to, rather than absorb, which is more passive. So volatile organic compounds are attracted to surfaces and certainly particulate matter, and especially the ultrafine particulate matter, and they attract to it and they get absorbed into your body through that pathway. Ozone is reduced, good news, 30 to 70%, depending, you know, on the home. If your air conditioning is on a hot day, you're really reducing the ozone indoors. However, it's not completely eliminated, and on a bad air day outside, it's also in your house mixing with the VOCs. So what do we got in there? We got particulate matter. We got volatile organic compounds. We've got semi-volatile organic compounds. We've got ozone in the house. Particulate matter is different. The VOCs and semi-VOCs are elevated. The ozone's reduced, just different. So what is this stuff? Particulate matter, some of it's natural. Some of it comes from human activity. Some of it comes from pollutants. The natural particulate matter, everybody recognizes this stuff. Dust. It comes from soil tracked in on by foot. Human skin, animal dander, dust mite droppings, particles from other insects like cockroaches, mold. So there's the mold spores, there's pieces of mold that are in the dust, there's components of the cell wall. I mention that only because if there happens to be a mold problem in your house and you're sick, the mechanism may be the cell wall components because they're what are called pro-inflammatory. So they contribute to an inflammation, especially if there's one already there. And then there's bacteria. This stuff is certainly not sterile. Human activity, movement, moving around, stirs the stuff around. Cooking. Cooking actually adds to particulate matter. Some of it's really obvious. If you're frying bacon, there's actually particles coming off from the oils and parts of the bacon into the air. But cooking adds to particulate matter anyway. If you happen to be cooking on a gas appliance, hey, who cooks on a really high heat? So you only partially, very slowly burn the gas as it's coming out so that so that you can cook properly. So you've got partially burnt fossil fuels in your home, adding to the particulate matter as well. Food particles, of course, the stuff that doesn't get caught in your beard. Tobacco smoke. If they're smoking, it is such an overwhelming pollutant that it's really hard to measure the stuff in the air. And if you live in a multi-family dwelling, an apartment building, and your neighbors smoke, some of that stuff is getting into your apartment. Burning candles, fabric fibers, all of these things add to the particulate matter. Contributors are things, they add to the quality of it. And saying the particulate matter is less, but it's different. You've got air freshener sprays, cosmetics, traces of metals that come in on your shoes and so on, from the soil. Volatile organic compounds are changing the quality. Semi-volatile organic compounds, again, adsorb, attracted, attaching particulate matter. Pesticides, fire retardants, plastics. Sources of volatile organic compound emissions: construction materials in your home, fabrics, furnishings, adhesives, glues, wall-to-wall carpeting, particle board, press board, paints, caulks. All this stuff is in your home. All this stuff is in your home and everybody else's home and probably at work too. Semi-volatile. As I said, they're just less volatile than volatile organic compounds. So there's significant amounts in the house, some of it in a gas phase, some of it in a solid phase. So that's more difficult to analyze. You need a different technology. So if someone comes into your home and measures the chemicals, they're probably not even measuring these. They occur as active ingredients in pesticides, cleaning agents, personal care products. They're major additives in materials such as floor coverings, furnishings, electronic components. So especially the fire retardants, they're by law, and it's a good idea to, if your house catches fire, that it burns more slowly so you have a chance to get out, etc., etc. But there's also stain repellents. They're on your furniture, the furnishings. They're on your carpets. They're on your clothes. They're semi-volatile organic compounds. They release very slowly from the sources. They're inclined to stick to surfaces, like particulate matter, and they can persist indoors for years. It's kind of similar to the outdoor persistent organic pollutants. They don't go away. And where do they come from? Well, we breathe them, we eat them, and we put them on our skin. We burn them. active ingredients in pesticides, cleaning agents, personal care products. The same thing over and over and over again. This is our environment, and we're not going to change it. Indoor levels of semi-volatile organic compounds are much higher than outdoors. And we have a body burden. More than 100 of them have been measured in humans. The average body burden is actually going up, not down. Plastics, phthalates, associated with allergic symptoms in children, retarded male reproductive development, altered semen quality. So these perfluorinated chemicals, what are they? Well, they're used as repellents. So they repel water, oil, soil, grease. We use them for paper and packaging. So, well, where would we use that for? Well, you go buy some chips from McDonald's. They're greasy. And so the cardboard is coated with this stuff so that the grease doesn't mess up the cardboard and it falls on your lap. It's used for rugs, carpets, and fabrics because we don't want to stain the things that we have. There's elevated levels in cord blood, newborn babies, and the more elevated it is, it's associated with low birth rate. And I say it's elevated, I didn't say it right, there actually should be none, but compared to when there are low levels, if the levels are more significant, if moms have more exposure to those things, she's more likely to have a smaller baby. There are also hormone disruptors, and some of you may have heard the term, maybe not. Hormones are chemical messengers in the body. We've all heard of thyroid hormone and estrogen and testosterone. These are chemical messengers that are produced in one part of the body and they give messages to other part of the body. There are man-made chemicals that disrupt that messaging system called hormone disruptors. Fire retardants and plastics, the semi-volatile organic compounds, many of them are also hormone disruptors. So when we look at ventilation, now look at the standards and guidelines that we have here in North America. They have the modest requirement indoor air should be acceptable to 80% of the occupants. That's where we get it from. It's not based on health effects. People go into your building or your home and say, oh, the ventilation's fine. This is what it's based on. It's not based on whether it makes you sick. It doesn't consider productivity or learning. So when they've actually gone into some of these buildings and jacked up the ventilation way beyond the guidelines that are recommended, people say, well, gee, you're wasting energy. It's costing money. Very true. But productivity in the workplace goes up and learning in the schools goes up when you increase the ventilation. The current building code standards and guidelines are based primarily on the practical experience within the building sector. They're not based on health-based criteria. They're based on, is the air acceptable for people who go in there. They do not consider the contamination of the indoor environment when they're getting the guidelines. So mechanically ventilated buildings like this one, you got to bring in the oxygen, you got to blow out the carbon dioxide for the people that are in there. There are obviously no windows in here, so they use an air exchanger. And they use the air ducts to move everything around. So it's based on the number of occupants. So if some of you go into your building at work Monday morning and go, well, the air sucks in here, and you go, well, no, it doesn't. The ventilation standards have been, are within normal limits and so on. Well, what have they done? Well, when there's less people in the building, they turn the ventilation down, and rightfully so with respect to wasting money and bringing in the oxygen and blowing off the carbon dioxide. But the pollutants continue to gather, so when you show up Monday morning, they have been ventilated less and they've gathered in the air. It's not, the ventilation requirement is not based on contamination. Most homes don't even have an air exchanger unless you go buy one. The modern homes, many of them, the brand new homes being built now, they're starting to put them in there, but most homes do not have an air exchanger. Homes that are heated with radiator or baseboards don't even have a duct system, so it'd be hard to even put in an air exchanger. So the only ventilation in many of these buildings is passive. It's through flaws in the building envelope, which have continued to tighten, but still they're less than perfect. So air does move throughout the building. So let's look at this room here. What would an engineer be likely to tell you about the chemicals in this room? And you just look around and go, oh, this is a lovely room. So we got treated wood, we've got all kinds of fabrics, we've got the carpets, you've got the couch, you've got the pillows. Maybe there's some mold in the logs in the fireplace. I don't know how long the plants have been in there. If you look on the table carefully, you can see the newsprint. Probably the Gazette marks your fingers when the stuff comes off, when it's fresh. And if that was my living room and it was Sunday morning, I'd be in there enjoying the peace and quiet with my laptop on, adding to the air pollution. So you bring in an engineer to measure this stuff in there. And he's going to measure the VOCs, and he's going to tell you, well, we only measure the total. We don't tell you what the individuals are. And where'd they get it from? Well, in the 80s and 90s, they took 22, and remember I said there could be hundreds of them, but they took 22 major ones, and they kind of played with it to see whether they could irritate people's eyes and respiration, and if so, they said, okay, well, we've got some idea of what the levels should be. That's all we have. So most of the time when they go and they measure the TVOCs, they tell you it's likely normal. So those of you who have certain buildings that you're going to go, you know, my building at work is sick. I have to go work in this building. And the engineer may go in and say, well, the TVOC is the same in both buildings, but that's the total. So we could have, I don't know, what do we got here, 100 people. We have 100 people here, and you go to a men's club and have 100 people. Obviously, the types of people that are in there are all males versus a mixed crowd like we have here. The total is the same, but the individuals are different. There don't have any Canadian or US guidelines. So they talk about target and action units. And so in other words, we'd like to see it around 1 milligram per cubic meter, but we get 5 milligram cubic meter. That's the number that they found in the challenge study. So they, oh, okay, maybe we should do something about it. Europe has decided to take a target of only 0.3. So what's the difference? Well, they have a difference of opinion. It's not based on studies. The individual chemicals, as I mentioned, are not identified. Most of those chemicals do not have exposure standards. So some of them do, but they're industrial. So where'd they get them? Single exposures, 8-hour days, healthy meals with protection in industry. That's where those standards come from. Semi-volatile organic compounds aren't measured. Ozone's not measured. The byproducts, they're called oxidants. When ozone mixes with other chemicals and makes new chemicals, we call them oxidants because they have a bit of oxygen in them. They're not measured. Low molecular weight aldehydes, whatever those are, they aren't measured. The famous one everybody's familiar with probably is formaldehyde. If it's reported, it gets measured and reported separately. Particulate matter totals are measured, but they don't tell us what's in there. They don't tell us how much plastic or fire retardant is stuck on it. The volatile organic compounds plus ozone produce particulate matter. We don't know whether that's that or whether it's a dead insect. The chemicals absorbed are not reported. Indoor air is a soup. And the recipe is you add contents constantly and you stir continuously. Right now, at this very moment, there's all kinds of stuff floating around in the air that we can't see, that we're totally unaware of unless it's making you sick because you're sensitive. But there's a dynamic going on all the time. It's not just sitting there. They're mixing and matching and making new things and more things coming out, and it's happening on a continuous, regular basis. That's the soup. So what are the contents? The same stuff, particulate matter, volatile organic compounds, semi-volatile compounds, other chemicals, ozone, biologicals, continuous reactions. You mix them in the air, they're producing particulate matter, they're absorbing to each other, they're being oxidized by ozone, and there's this thing called surface chemistry. So what's surface chemistry? Well, when I went to high school, you put stuff in a test tube in chemistry, you put in substance A, you put in substance B, and then you heated it up so that the molecules would start moving around like crazy and bang into each other. And therefore, they were more likely to create a new substance, and hopefully it didn't blow up. Indoor pollutants react with each other. It occurs in the air, but also on surfaces. There's this thing called surface chemistry. The surface increases the likelihood of reactions. It provides a place for them to meet, like a dating service. It brings these things together. Surfaces speed up the rates of reactions. A large surface area indoors compared to outdoors, just like if we were out in a meadow, we wouldn't have all these chairs. So there's a bigger surface area indoors compared to outdoors, providing a substrate or an attraction for the chemicals to mix. So they speed up and they help stir the soup. And the surfaces include walls, floors. Your skin and your respiratory tract are a surface to help these chemicals meet and mix. So when you add in the ozone, 30 to 70% of outdoor levels, reacting with the chemicals indoors to produce more toxic chemicals. So we have an ozone gas phase. It reacts in the air with the volatile organic compounds. And it reacts with your personal care products. There's a thing called near head chemistry. So when the people go into the building and go, well, let's measure the air in here and see what there is, we make an assumption that that's exactly what we're breathing, but actually it's not quite right. We do breathe that stuff in, but we also breathe the stuff that's coming right off us. The surface phase. It also reacts with natural things like human skin, the oils, our clothing, were they dry cleaned? Do they have